who is an associate professor in the Department of Electrical and Computer Engineering at UTSA. And she's also the Vice President for Securing Automation and Secure Manufacturing Architecture for Mechani, which is located in San Antonio. Her expertise is in anomaly detection, distributed alert correlation, network and application level security, cyber physical system security, and also distributed system security. So before joining us at UTSA, Gabriela was the Chief Product Officer at Alpha Secure and also a Senior Technical Manager at SRI's New York City Research Hub, where she was focused on cyber analytics, which she has established in 2016. And she has a wide range of experience in research programs with different DoD organizations, including DARPA's Transparent Computing Program, ARL's Internet of Battlefield Things program, and several other commercial and Department of Homeland Security projects. Gabriela holds a PhD and an MS in computer science from Columbia University and a bachelor's in computer engineering from Polytechnic University of Bucharest. It's indeed a pleasure to have her here to share some of the exciting things she's been doing on the security side. Welcome, Gabriela.
Thank you so much. Thank you for the nice introduction. And let's start. So today I want to talk about the fact that everything that we see around us in terms of technology is actually connected. Security and reliability are two things that are very important, and they are very important especially for critical infrastructure. So let's see what I mean by connected research areas. I've been doing a lot of work in smart contract verification, in cellular network, in monitoring behavior and properties of IoT devices, IoBT, secure manufacturing. All of these are critical infrastructure that are actually not working in isolations. They depend on each other in some cases, and they are using techniques and they are using technology underneath that is quite connected. So why do I even say that everything is connected? One first thing that we should think about is that critical infrastructure is becoming more of a target of attack. So we are seeing more and more threat actors trying to get to information technology networks. So these are the networks that are normally not visible, but now they are becoming more and more visible on the cyber physical system side. So imagine industrial control systems. So the IT side is actually on the control system side. And then all these different critical infrastructure elements are targeted by attackers. DHS has been noticing that in 2020. And we are also seeing that there is a dependency between critical infrastructure that actually make other critical infrastructure suffer degraded performance. So, for example, mobile use is actually extended to industrial IoT systems. So if something happens in the cellular networks, there will be an immediate impact on the actual critical infrastructure using the cellular networks. Of course, there is redundancy in some cases, but there is definitely an impact there. And then critical infrastructure is all about this idea of cyber and physical systems. We cannot treat the cyber and physical aspects in isolation. And throughout my work, I've been looking at both. So let's look a little bit at security. I mentioned that I will talk about security and also reliability. So when we talk about IoT systems, I've been looking at multiple ways in which we can monitor the behavior and properties of IoT devices. And I had a lot of publications with colleagues of mine. We looked at device identification and monitoring, modeling cyber physical attack paths using formal models. I looked at causality events in IoT networks. This is something that was also an extension from my work in transparent computing, for example, where we were looking at causality within enterprise networks. So I've done a lot of work like this, but today I want to talk about a particular approach that we've taken and why we've taken that approach. So when we talk about IoT systems, we talk about systems that are under attack. And these are just a small sample of attacks that have been happening throughout the years. One interesting one when we are talking about industrial IoT is this hacker that used evil bubbles to destroy industrial pumps. So they sent bubbles in such a way that the industrial pumps were physically harmed. Then there were these interesting attacks where inaudible ultrasound commands were used secretly on Siri, Alexa, and Google. Now imagine that you are at home, you have your device, and you have the TV running some type of commercial, which also uses ultrasound commands, and suddenly your devices in your house start to do things that were not supposed to. And then there were also all sorts of very disturbing attacks on kids' toys and kids' cameras and so forth. So those were very, very targeting kids, and they were extremely impactful on kids' health in a way, and so forth. So as you see, there are so many types of attacks, and IoT becomes like very, very important to support and to research. So our big question with one of our work was, how can we know if IoT devices have been exploited? You have your IoT devices around your house. How do you know that certain flaws are not already in your IoT devices, in your house, in your office, and so forth? So as we know, there have been already a lot of types of attacks that have been exploited on smart home devices running Bluetooth, Zigbee, and Wi-Fi. These are the main three protocols used. And how do we find out if one of our devices have been exploited in a generalizable way? So we wanted to see if we can find monitoring capabilities that can be applied across multiple types of devices. So we created this system called loTHound that is doing this device identification and monitoring. And because we are talking about network traffic across Zigbee, Bluetooth, and Wi-Fi, we actually studied all three. So we were able to detect anomalies in network traffic by observing clusters of behavior over time. And we also wanted to see if we can estimate the location and use physical properties for estimating the location of devices in a physical space. And in terms of the evaluation of our work, we built a testbed with 21 commercial off-the-shelf IoT devices, and also we used a data set that was publicly made available in one of the top conferences, IEEE SMP. And then to actually run the anomaly detection component, we had to create again a nice testbed. We used a Philips Hub component, and we also had a small network of Raspberry Pis where we could prove our points. So what was the system overview that we created? So we have a sniffing device for Zigbee, and we were also looking at Android phones and being able to tap into the Bluetooth, and also, of course, the Wi-Fi traffic. And we extracted the RSSI features. These are features that are telling us how strong the signal is to actually help us estimate the direction. So if you know how the antenna in antennas, the Wi-Fi antennas, for example, in a space are distributed, then you can actually have an estimation of the direction. And we were able to see where our devices stay in the physical space. And we were able to do identification and anomaly detection. In terms of the direction estimation and the device type of identification components, we put them all together and we created an anomaly detection module and a UI so that a user can actually see what's happening in their network and can see the types of devices that they have, they can see the network flows and all the anomalies that are observed in that network. Let's go a little bit and talk about the device type identification. When we talk about IoT devices, we talk about devices that have predefined type of behavior. So I would not call them repetitive types of behavior, but in a way they are like that. So when we created a model for the devices, we used a set of features like inter-packet time arrival, payload length, payload entropy, and packet entropy. These are all indicative of the types of communication that the device is actually doing. And then we had statistical values for all of them. So well, imagine that when you have Google Home, for example, there are certain types of packets that are sent also to the servers that the Google Homes communicates with. We can definitely analyze all of those and understand what is the behavior actually and what are the types of communications that are happening. And then in order to see what how much time do we need to actually capture a behavior of these systems, we calibrated this time window value by distinguishing between the different types of devices. So when we talk about two devices, for example, there is a functionality of a hub. So a lot of the home IoT devices have a hub, and then they have all sorts of sensors. There is a communication between them, and then we can actually see what is a central point and what is an endpoint device based on the communication patterns that we see. So we were able to differentiate between them, and then we use HDB scan clustering analysis on all these extracted feature vectors to actually capture the behaviors. And when we talked about device direction identifications, we had routers with N antennas, and for any N antennas, you actually have N multiplied with N+1 divided by 2 possible pairs of antennas, right? So we find that by using a differential signal strength, we could actually model those, and we used SVM for modeling, and we trained 2 types of models with 8 smartphones. So we wanted to see how accurate can we be in terms of the direction if we are using only 4 directions from the router or 8 directions from the router. And you will see that the results are telling us that there are certain limitations because of the types of signals that we were analyzing. And in terms of the anomaly detection component, as I mentioned, we were building these clusters that a particular device would generate. So we cannot think of one behavior for a device. A device will have multiple behaviors in a way. And we stored all these cluster centroids generated. And then every time the device would interact afterwards in the testing phase, we would see if there are deviations from that particular cluster of behavior, or if they are not even seen anymore. So in terms of the evaluation of our system, what were the questions that we wanted to answer? We wanted to see if the clustering technique was able to cluster different devices of the same type into the same cluster. So interestingly enough, if you have 3 Google Homes, they will actually behave very similarly. They have the same kind of network interaction, and we were able to capture that. And then we wanted to see, is our technique generalizable for other data sets? We used a completely external data set to answer that question. And then can we detect the direction and direction changes of devices effectively? How well will that technique work? And can we effectively detect various anomalous scenarios? So these were the different types of analysis that we created. So for the device type identification, we collected Wi-Fi traffic for 7 hours. And for all of those 7 hours, we were able to achieve average clustering accuracy of 99%. These were the different types of devices that we analyzed. These were the number of packets that we had, and these were the number of examples that we have and the overall clustering accuracy. And we had a similar success across Zigbee and Bluetooth with averages of 97 and 90% averages. That means that there is a certain pattern in how these devices are actually interacting with each other. This is this is how our clustering performance looks like when we started increasing the collected data. So we wanted to be able to do this type of analysis within a very small time window, because IoT devices can be on or off the network. So we wanted to see if that's going to be the case, and if we get more data, if we improve significantly. And as we see, there is not having 2 hours of traffic was more than enough to actually achieve the results that I was talking about earlier. And then we also wanted to apply our technique on a different data set. So we took this data set that was made publicly available, and we applied our technique without changing anything. And we were able to have clustering accuracy very similar to the ones in our network. So we had 3 days of data for those, and we analyzed the 3 days separately, and we were able to achieve very high performance there as well. And then when we talked about the device direction identification, we also collected data for 2 days and 1 day in 2 different office spaces under normal operation. So I would have to add that the RSSI signals are actually pretty sensitive to the geometry of the space. So if you have, for example, in the office, when we were analyzing this, we had certain very thick poles. So we were very careful where we set up our targets, so that we can capture as much of the space as possible. So yeah, and then results also deteriorate drastically with less data. So one thing that we noticed is that for 4 directions, we were able to have very high accuracy. When we looked at 8 directions, the accuracy actually went down. So we cannot distinguish, when I'm talking about 8 direction, it means distinguishing with much more precision, and that's not possible with RSSI signals. There are other signals that can be analyzed similar to what Ioannis actually presented last time, and that's when we would have a better precision than RSSI. Let's move to the anomaly detection part. So when we looked at anomaly detection, we set up different scenarios. The first scenario was the base scenario, was when nothing was happening. The second one was for all these Raspberry Pis that we had, the 7 Raspberry Pis, we actually used a cryptocurrency miner on one of them. Then we ran completely different protocols across the Raspberry Pis, and then we had IRC bots in scenario 4 for devices, for 2 of the devices. And just our data indicates that we were able to distinguish between all the different anomalies that were happening in this Raspberry Pi network. But one would say that that's not sufficient, because this was a setup, a testbed that we were setting up ourselves. So we had to, I will show more results from that. So in terms of a Philips Hue bridge that we knew that has a particular vulnerability, we exploited that Philips Hue bridge, and we could actually show that the behavior, so this is the blue is the normal Philips Hue bridge, and the orange, the exploited Philips Hue bridge is the behavior in orange. So we can definitely see that there is a significant difference, and that was a vulnerability that was in the wild, and we were able to detect it. So this is a stronger result in some regards, because we had no interference with the system. So this was one tool that we built where we use cyber and physical properties of IoT devices to categorize and monitor such devices, and we were able to effectively determine the direction and to identify different devices. So when we had a class of device identified, and then we also had the direction estimation, we were able to distinguish between individual devices. And then we were also able to do the anomaly detection capability on top of that. So now this is security. Let's see what it means to have reliability. As I was mentioning earlier, cellular networks a lot of times are used for supporting other critical infrastructure. I've been doing a lot of work on cellular networks, doing anomaly detection, doing verification, and looking for changes in network, and then sharing knowledge across cellular networks, so that you can use diagnosis information from one network and apply it into a different network. Why are cellular network interesting? Because, for example, smart airports are going to switch to cellular technology. When we are talking about 5G, IoT, and the new supply chain challenges, we are going to move into the cellular networks usage for tracking supply chain. And interestingly enough, NASA and Nokia are actually putting together a 4G cellular network on the moon. So cellular networks are extremely relevant. And with our work we've done, we started very simple. So this was a collaboration with Nokia Research. And we started with some key performance indicator data from different types of cells that we had available. And the idea was, can you say from these key performance indicators if the data collected from all the different cells that we had available is actually indicative of a cell anomaly? So we started simple, and the main objective was to figure out if something happened, something changed in the network. Operations changed over time, system configuration changed over time, and all of those had some impact on the performance of the network. And the first idea was to characterize a cell based on these key performance indicators. I'm going to define a few of them in a little bit later. And the first idea was, can we do a diverse set of models, and then see if we can put them together and build a model out of the different types of models. So we also use visualization capabilities to have a situational awareness, and we also allow user input to help us investigate this anomalous behavior. So the idea was to use an ensemble methods approach, putting together all the models, use the models to in a voting scheme, and then figure out which model has a better performance by using context information. So we had, aside from the key performance indicator, we also knew if some changes are happening in the network. So we had events and maintenance information and configuration changes information that enable us to say, oh, this is this model gave us a better input than others. And initially we had a very small data set. We had 70 cells on a live mobile network. We had 12 KPIs collected every hour. And what I mean by KPIs, these are measurements of user traffic utilization, downlink, uplink data volume, and then the measurements of call control parameters, drop call rate, how many calls are dropped in for a particular cell, how many successful call setup rates are done. I just want to remind everyone that this is data that is aggregated data. So there is nothing about the user in an individual user in this data. It's all aggregated on one particular cell in an area. One challenge that happens a lot of times in both security and anomaly detection in general is that when you have real data, a lot of times you have no ground truth associated with data. So we were again in that position, but we were also lucky to have expertise that helped us discern what types of events were happening in a particular network. So to be able to evaluate the performance of our models, we actually created a visualization tool where we could see what's happening in a particular cell with respect to a particular KPI. So we were able to actually mark manually all the data. So we had to label all our data to be able to detect when things were going wrong. And we were also able to verify against the different context information that we had. So by doing that, by using the contextual information, that became also a trigger for our analysis. So every time we knew that we knew that there was a configuration management change, then we could actually readapt our models and train new models every time that was happening. But also detect the fact that there was a configuration management change. And then overall, the performance of our ensemble method ended up being close to 80% detection rate with a false positive rate of under 5 or so. These were the different types of methods that we tried, very simple methods. This was the first analysis of the data. Then later on, we started to look into more complex ideas. What the topic that we were interested in was called SON coordination verification. So again, networks can suffer degradations if actions that change network element configurations are not coordinated. So imagine that you have a network with thousands of cells, and if you make one change in one cell, you can definitely have an impact on the cells that are neighboring cells. So we wanted to see if changes that are happening in a network will have a negative impact on the overall health of the network. So we introduced this idea of SON verification that must occur fast in order to correlate the detection results and diagnosis of the system. So the key problem that we were addressing then is how do you model a network or a subnetwork state? And we used a very unusual approach for this problem. So there is this method called topic modeling that is a very well-known approach used for discovering and annotating large archives of documents with thematic information. So extracting the topic of a particular article or book or whatever. Well, we took the same idea and we applied it in our network. So discover the topic states in a cellular network. And we wanted to determine the number of states automatically with using HDP. So for a given network, we wanted to see, oh, these are the different states, given the different KPIs, these are the different states, we can call them clusters in topic modeling, they're not called clusters. These are the different states in which a network can be at certain times. And it can be a mixture of those states based on the cells that are in focus. So we started from LDA model, which is a very commonly used topic modeling model, where the circles are random variables, the shaded circles is an observable, in our case is our KPI feature, and then the model is actually a collection of m timestamps of KPI data from our n cells. So at each timestamp, the KPI data is represented as a mixture of k, right? You can have multiple states at the same time. And the goal was for it, we wanted to achieve for each cell n at time n, the KPI feature W can be classified into one of the K clusters. So we wanted to see what is the state of the network. And LDA is great, but it has one drawback, the fact that you have to know the number of clusters ahead of time. So then we switched to HDA so that we could determine the number of clusters automatically. And to do that, we actually added on top of LDA a layer that enabled us that contained the random variables that control the number of profiles across the network, the ones that we wanted to discover, and also the number of topics. So then with this approach, we were able to determine the number of clusters of states that were in a network. So let me show you a little bit what we mean by states. So once we were extracting for all the different KPIs that we had, once we were extracting these particular states, we also had to interpret them. What does it mean to have a state where this is how that look like this? So here we have a state where this particular KPI is a drop call rate KPI. No, a drop call rate is good if it's close to 0. So this looks like a very stable drop call rate because it has values around 0 most of the time. Same here. It's another it's also a drop call rate, which is good. It's not very good, but it's very reasonable. But when you have a drop call rate like this, it means that the network is in distress, for example. And then if you have a call success rate that looks like this, again, the network is pretty bad, because you would want to have a call success rate of high value, right? So we had a way of actually classifying automatically the state of that we were identifying with the topic modeling, and based on those we could determine overall if the network was in a normal or an abnormal state. And then when we were testing the system at every timestamp TK, we were building a set of mixture weights, right? And those were indicating overall if the network was in a good state or not. So that was one of the things, right? We were able to determine if the network is good or not, but we also wanted to understand why is the network in a bad state. So for doing that, we used Markov logic networks, which are first order knowledge bases with a weight attached to each rule. So imagine that you have these rules. This rule says that anybody who smokes could have potentially cancer. every rule like this has an associated weight, and the beauty of MLNs is that they also support the contradictions and also support missing data. And indeed, when we talk about different types of diagnosis capabilities, we might also not have access to all the data for cellular networks. So we needed something that had both contradictions and missing data capabilities. So then MLN is going to give us the most likely explanation for a given event data. We also happen to have a very good state-of-the-art MLN solver while I was at SRI, so we used that particular solver. And then this was a new thing that we combined in the MLN and the topic modeling to do detection and diagnosis at the same time. So we use the network state information extracted from the topic modeling in the MLN inference. So when we were talking about the number of cells, we had a lot of cells. We had thousands of cells. Doing that at the level of each cell was taking too much time. So then we had to use principal component analysis to identify the groups of cells that had similar behavior. We collapsed those, and then we reasoned over those groups of cells to reduce the number of entities that we had to deal with. And then the MLN provided the most likely explanation for the state of the network. And what was the, we were reasoning over configuration management changes, so configurations that were done in the cellular network, and external factor information, and more specifically on weather. Weather can actually have a significant impact on the cell health and cell performance. This time we had many more cells to work with. We had a Trige dataset over 3 months. We had 9,000 cells. So this was a much bigger data set than we originally had, 120 or so. And we had 11 KPIs to play with. The call success rate and the drop call rate can be analyzed at the different phases in the process. So we had we also had other types of KPIs. And we had missing data points. There were missing data points. Again, we didn't have ground truth information with the provided data set. And we had hourly KPIs and daily CM data. So the fact that they were not even aligned, that made it more difficult, right? The fact that we had hourly KPIs, but daily CM data, we couldn't see perfectly into the reasons that were happening into the network. But even so, we had some very good results. So when we applied the topic modeling on this large network, we were able to extract 32 topic modeling states from the process. 15 of them were labeled normal, and 17 of them were labeled abnormal. Again, based on these characteristics that I was saying earlier, if your call success rate has to be high, and the drop call rate has to be low, and so forth. This is an example of an abnormal state, because we have these two KPIs that are impacted in the call success rate. And this corresponds to a particular anomaly condition in mid-February. And you'll see why. And then when we looked at those anomalies, we wanted to map the anomalies into MLN, and then see if we can find what cells were particularly affected by an external event. And the types of events that we had, again, were configuration management data. And guess what? We found something extremely interesting in our data. We found out that the angle at which certain cells were set actually changed. And those angles made the cells lose their performance. And this was a very, very interesting result. So we were able to identify the groups of cells that were affected from the angle changes overall. And again, this was CM data, configuration management data, that was collected hourly versus was collected daily, I'm sorry, versus the hourly KPIs. So this was a very, very interesting result. And then this is how, if you look at the percentage of cell representing the change, the configuration management changes, we can see that this is when the event happened. So these are the different cells actually starting to misbehave. And then we also had a different angle that we looked at with the weather information. So we were able to see what cells were impacted by weather. And we could see that there was a particular weather event because we had the weather information, and we could see that the performance of those cells has degraded. So that was also an interesting result that we got. And just to look at the summary of this approach, so we were starting with this KPI data. We generated the topic modeling that led to these clusters. We should not call them clusters, really interpret the semantics of the different cluster, label the cluster, test the KPI data against the clusters that we had, and then achieve a weight mixture indicating the current network state. If the state was anomalous, we were then analyzing the configuration management changes and the weather events using the MLN rules, and be able to distinguish between the groups of cells that were impacted either by configuration management or weather events. We also had a nice visualization where you could see the different cells that were impacted. So this was a research that spanned 4 years. These were just 2 of the results. We had more, but as an idea, the cell anomaly detection, we tested on KPI data for a real operational cell network. We had good detection performance. We were able to cope with concept drift problems, and the approach was suitable for practical use. And then on the SON verification, we tested on a much larger network. We had configuration management and weather data. We applied topic modeling in a completely new setting, and we also combined topic modeling with the MLN in a new setting as well, and we got very, very good results. So this shows this work shows this idea of reliability. If you don't have networks that behave normally, then suddenly you are losing your performance. You are losing the ability to rely on the cellular networks for critical infrastructure, and that's how the two of the works are actually related. Okay, and I'll stop here, and I'll take questions. I think. Not sure if there are questions already, or maybe you want to ask them directly.
Professor, this is Velu. I have a question.
Sure.
So regarding the directional experiment you did, I'm trying to understand, is that for finding out whether the intruded net device is coming from a different direction than all the other preset trained devices?
So one thing that we discovered in our work was that if you have 3 identical type of devices, they will be clustered in the same way. So then it's very hard to distinguish between them. When we use the RSSI approach, if they were set up in an environment in different places, we were able to say, yes, this is one device, this is another device, and this is the third device. So we were able to identify that there were actually 3 different devices in the room and where they were located. That's what the identification part comes into place, because or just with the clustering approach, we were able to have classes of devices. And the RSSI work gave us also individual device level monitoring.
I see. So in that case, are you expecting this intruder device to even spoof the MAC ID? Because you can.
We were not relying. So we were not relying. That's a very good question. We were not relying at all on the MAC information. So we were just relying on the behavior of these devices. So yes, an attacker could actually change. Actually, devices are changing their own MAC addresses, by the way. They are done like that intentionally so that people cannot track them based on the MAC address. So yeah, we should not look at MAC address to necessarily identify a device. And last week talk was also showing that doing RF fingerprinting is much more beneficial than anything else in tracking devices as well.
Yes.
But you cannot do anomaly detection with that approach. So it has, it has a different use.
Okay, thank you.
Thank you.
I have a question. I don't know if I sound choppy. My internet's kind of bad. So should you apply this to like an industrial control system, how quickly could you detect all devices that they have and like identify like their network traffic and like the type of device that it is?
As I said, we were able with only 2 hours of data to characterize the devices. And then we were able to quickly determine if the clusters were changing. So it can be used. It's not going to be real time. It's fast enough to be used in a near real time setup.
Okay, cool. Because I guess I suppose with I forgot the attack that happened over the summer, but some companies, they do become targets to individuals interested in seizing their entire system. So I was wondering if this could be applied either before that happens and seeing if there is an anomaly in their network, or even after their system is seized and maybe they don't have to pay, they can just use this instead, just like get rid of all the devices that have been affected.
Yeah, this also has another role. Yes, I totally agree with you. This also has can help with something else. If you have a network and you don't know exactly what devices you have in the network, this can also do asset management in some regards, because you can actually notice all the different devices in your network, which is one of the issues, right? How do you know that? For example, if you have an office and you share this, you have another office next to you, how do you know how many devices you have in a particular environment, and how do you know that somebody else is not trying to use your environment and so forth? So it also gives you the ability to identify the devices and also the directions from which they are coming.
Very good. Thank you.
Thank you.
I had a question. What kind of tool did you use for the traffic analysis?
We build our own. This was we build our own analysis, right? We were using HackRFs. We were using, if that's what you are asking, the types of we used a particular phone to capture the Bluetooth, and we captured the traffic, and then we analyze it ourselves. So this whole system has been built. I had 2 summer interns working with me and my colleagues, and we had a lot of fun. So we built everything from scratch.
Okay, thank you.
Thank you.
I have another question. So
Sure.
Wi-Fi and Bluetooth and Zigbee, are all these three? I'm not very familiar with the Zigbee. Are they directional, one-to-one directional, or can you get a reflected signal, at which point you don't really know the reflected signals?
That is a good question. We haven't looked into that at all, but let me come back to that question because I don't think I'll have to come back to you on that. I don't think they are reflective, but let me double check.
Yeah, I was just as a continuing. I was just wondering the same device, but at some point it'll go through a wall, which the signature.
I understand what you mean, but I don't think that. But that's a very good question. I don't think, if you are talking from the RSSI's perspective, right? I think the signal is not that strong to actually be able to go to that point. So yeah, I don't think it would have a reflective attack, but but let me double check.
Okay.
It's a very good question, actually. You want to see if an attacker can actually mess up the environment by doing that, right?
Yes, exactly. So because some of, if I take a home, there are devices that are very static, like TVs and probably Alexa, but there are mobile devices like not even your cell phone, but like a robo, Roomba. Roomba is going all around. So and then a vacuum cleaner, right? So it is very mobile. It is a home device, but the signature is going to change because it is going to go from room to room. And
yes, and then you might also change the you might have multiple connectivity points in your home. So then
these days there are multiple routers sitting in a home. So
fair enough. That's a very good question, actually, for the RSSI part. Excellent question. I'll have to think about it though.
Thanks.
I think we would have to change the approach and then analyze based on all. Change a little bit the environment. Maybe right when we put the 4 or 8, when we were measuring for 4 or 8 directions, we were assuming in one space, one big space, you have these 4 or 8 directions. So you have to replicate that in multiple rooms, because now you are starting to, and then you have to model with respect to each room.
Yes, that's right.
That's
because
correct.
just yesterday or this week, Amazon just launched a new device called Astra.
Yeah, I saw it.
Astra, which is going to move around the house all over the place. So and
that's true. That's true.
Powerful device. So
that's true. Well, for now, I'm not sure what they're going to do with it. It's for now, it's just a moving Amazon Echo. We'll see what other capabilities we'll have in the future.
Yes.
Yeah, thank you. Excellent question. Thanks a lot.
Sure, thanks.
Okay. If we don't have more questions, we can stop on almost on time.
I had another one. I just wanted to confirm. Do you think this type of analysis can be done by some like tools that have been like something like Wireshark?
Yes, with Wireshark, you can definitely analyze the Wi-Fi traffic, and Wireshark. Everybody who does network traffic analysis will use Wireshark to confirm things and to analyze things. But you are saying to have a plugin into Wireshark to do this type of analysis? Is that where you are getting to?
Yeah, kind of. Like.
Yeah. It could be. It could be an option. Thank you. Okay, I think we will stop here for today. Thank you all so much, and have a great weekend, and see you next week. Thank you.
Thank you.
Thank you.
Thank you.
You.